So I remind you the MCT, what we call as Lebesgue's monotone convergence theorem. Very simple. It says if you have a sequence of non-negative measurable functions on X, the value could also assume infinity. And if the sequence is increasing, and if you assume the limit of Fn as f, as you know, it's pointwise. We are always talking about pointwise. Then this f is in L plus. Actually, we have figured this out earlier. The real point is that the limit goes inside the sign of integration. That means the integration of limit equals to limit of the integration. So this is what MCT says. And I told you that it is one of the most fundamental results in mathematics, not only in measure theory or others. Okay. All right. So today, so this is what I said. So MCT is a real deal, and out of many, right now I'm going to show you one. So one more time, this L plus, as I said, is all those measurable functions from the set of all measurable functions from X to 0 infinity closed. Okay, this is positive, and that's the reason I have said plus. And this is what we'll use this without mentioning this, and you are also going to use it in entire of this course, even after today's lecture. Okay, so it says very simple. Suppose f is in L plus, then you are going to find a sequence of simple functions such that, you know, simple function, it's increasing essentially, so it increases to f. So you're going to find a sequence of simple function phi1, phi2, phi n, etc., such that phi n converges to f pointwise, and the limit, you know, this is f is going to be your limit. So integration of f is equals to limit of n goes to infinity integration of phi n over x. Now you just one comment, given f in L plus, you already know this happens. Up to this level, we know this, right? We know all about this result. We prove that any function of this type, f, you can always find a sequence of simple increasing sequence of simple function which converge to f. So this is our old result, but the MCT assures the last part. So MCT assures this to this. So it says not only it converges to f, but also the integration of f is the limit of n goes to infinity phi n. And that's one real deal. You know, when I introduce the definition of integration, you remember what is the definition of integration? So the left-hand side, the integration of f over x by definition is what? Maybe I try to write. So it is in sup of integration of phi over x, right? Where 0 less than equals to phi less than equals to f, simple measurable. Correct? Remember? So this is the left-hand side by definition. And at that point, I told you this definition is little difficult. Why? Because when you define in this way, you are essentially down to compute the supremum of a set which is of this magnitude, right? So it's not easy to compute such a supremum on all over simple function phi such that it have, you know, this inequality holds and. But look at this theorem. This theorem straight away tells you, it gives you relief. It tells you that you don't have to worry about all this supremum, etc. You just procure this sequence, monotonically increasing sequence of simple function, which we did in principle, right? Remember that sequence phi n was quite explicit for given f. So you look at that, and instead taking the supremum, you just take the limit, and that's going to be the value of your integration. So I hope you understand. This really gives you lots of flexibility from computation point of view. And in mathematics, if you can't compute it, it's not useful, you know. So this really make good sense. So any question on this corollary? And you are going to see this application again and again. All right. So if not, move to remark. This is again algebra or arithmetic of the extended real line. So we know, if you remember, we proved that if f and g are complex valued measurable function, then f plus g is measurable, right? I mean, it forms an algebra, I told you. But keep it in mind. In that part of the lecture, I pointed out it's complex value. That means I carefully avoided the infinity trouble. Okay. Now you see, however, due to the fact of that my plus infinity minus infinity is undefined, we haven't defined this. This doesn't make sense. Okay. So if infinity minus infinity is not defined, then if you consider f and g on the from x to the entire extended real line, that means minus infinity to plus infinity, then f plus g need not be measurable, right? Because f plus g need not be defined even. You understand? Because at some point x, fx could be infinity and gx could be minus infinity, and in that case you will be in trouble. So f plus g need not be measurable, or I might want to say f plus g need not be defined, may not be defined even, may be undefined. You understand? It's because if you have these, then this trouble might occur, correct? However, if you look at only the half, if you look at the 0 to infinity part, not minus infinity to plus infinity, then it doesn't create any problem. So you know that infinity plus infinity is going to be plus infinity. So in this case, f plus g is measurable, and this proof is just no difference the way we did in this case. It's just the same thing. Okay, infinity is considered as a, you just consider the in the neighborhood of infinity as r to infinity. R is a real number, and that way you can do the same thing. There is no difference. So one more time, as long as you can avoid these controversial things, that means undefined thing, you are good to go. Okay, and so this is something you have to be very careful about talking infinity. Okay. Fine, so this is good, and we are in this setting. We are not in minus infinity to plus infinity setting. So all I wanted to tell you, don't worry, we are going to be all right as far as our present setting is concerned. In today's lecture, from tomorrow, it will be a little different. Then you just keep this in mind. When you see that, you have to be careful. Here is a theorem which is just an application of MCT, but very, very important, and you are going to face this again and again. And it is now even more general, setting is more general. Okay, so again you start with a sequence of measurable function, non-negative, and you consider f to be the sum. Since infinity is there, you are free to talk all these things. Okay, so f is the sum of fn, then the result says that, I mean, if this is the assumption, the result says the sum is measurable, and the integration of f over x. So this is measurable. So this is also in a sense integrable, and the value of this integration is the sum of the integration. So this is the consequence of MCT, and we are going to talk about it. So the statement is clear. So one more time, you have just any sequence but non-negative. These functions are non-negative, and you look at the sum is going to be measurable, and the integration of the sum is sum of the integration, right? That's the right way to put it up. Integration of the sum is the sum of the integration. Here you go. The proof, I mean, the measurability is very clear. Measurability of f. So how you get f? You get f because you look at the sum of fn. How you get the sum? Remember, it is just the partial sum. So you look at the partial sum Sn, where Sn is the nth partial sum of Fm, all pointwise, and then you just take this is going to be increasing sequence, is it not? So this is going to be increasing sequence because you are dealing with positive function. So it is going to converge to fx as n goes to infinity, and we know in this case f is going to be measurable. So that part is very easy, no problem. We have to prove this equality, and that's why we have to work a little more and with a little care. Okay? That's the thing. You have to do a bit carefully when you deal with this, because having infinity is sometimes good, and that also creates some problem. So you have to be careful. So here you go. Since we know Sn is monotonically increasing and it converges to f, right? So That's the observation here. By the above corollary means, you know, any integrable function, you can evaluate this in this way for some increasing sequence of simple functions. Okay. So by above corollary, for all m, so what you do now, you fix an m and you look at fm. So fm is in L plus, right? fm is in L plus. So you are going to get a sequence of simple function, increasing sequence of simple function, which converges to fm, and subsequently the integration of fm can be computed by just looking at the limit of the simple function, integration of the simple functions. Okay, is it clear? So since my m is fixed, I have considered the sequence of simple function as phi1 m, phi2 m, and so on. So this m represent this m, and this 1, 2, etc. represent the sequence, right? All right, so you, for each m, you have this as well as this. The point is, once you have this, you can rewrite Sn in simple as a sequence, as a limit of simple function as follows. So you look at Sn, by definition, it is sum of fm 1 to n, and your fm is what? Fm is limit of phi k m. So fm is limit of phi k m, and your m runs from 1 to n. It's a finite sum. Since it is a finite sum, push it inside. So limit goes out, limit k goes to infinity, k is over here, and m, this index is a finite, so m equals to 1. So your Sn is this, right? Once you know this, then you further observe your phi mk. Of course, they are all positive. So for all k and even for all m, your phi mk is non-negative, and it is increasing. So this is less than equals to phi m of k plus n, k plus 1, and they are all dominated by fm. So you know all of it, right? If this happens for all k, then look at this sum now. This sum will be also increasing, non-negative. So for each n, this sum is going to be non-negative, and this sum is going to converge as k goes to infinity. This sum as k goes to infinity is going to converge to Sn. So this sum as k goes to infinity is going to converge to Sn. So what is that? I know, but what is this sum of fm equals to Sn? That I know. And converges, oh, I see. So this converges to the sum of fm, and that sum of fm from 1 to n, we know, is nothing but Sn, right? Fine. Now you appeal to the MCT, the monotone convergence theorem, since Sn, right here, since Sn is the limit of increasing sequence, all this thing is to set up the stage for MCT, okay? So you look at this and you prove this is an increasing sequence of non-negative simple functions, right? This guy. So now, not simple is also not needed, but I think it is simple, but not needed for MCT. So now you can appeal to MCT. Oh, I'm sorry. Yeah. I mean, this is simple, but for MCT you don't need. So integration of Sn is going to be limit of integration of this sum, right? That's MCT. So you know the integration of Sn over x as the limit of the sum of limit of the integration of sum of this phi mk, the simple functions. Okay. Now you look at the right hand side. By the way, what is the end? We have to take the limit here at some point, correct? Because and we have to take the limit here and push the limit inside to get the sum, right? The sum of fn. We'll do that. But the right hand side, let's observe this. If you look at the right hand side, then it is limit k goes to infinity of this guy, no problem. But then since it is again a finite sum, you take it out. So this comes out and your limit goes in, right? So this is limit k goes to infinity of phi km, but we know this is nothing but integration of fm, correct? So this is nothing but integration of fm by star. What you are saying, all in all, that integration of the Sn This is the nth partial sum. So integration of Sn. I do not know why I said this Fn again, but this is also your Sn, no problem. Maybe double it, no problem. Okay, so this is your Sn. So integration of Sn is equals to nothing but m equals to 1 to n integration of Fn. So this is to get this, which apparently looks very easy, right? Apparently looks very easy. What you did, you appeal to the sequential approach, right? Do you understand what I'm saying? For simple function, if Fm are simple, then we know this equality is true, correct? But Fm right now in this consideration need not be simple. It's general measurable, non-negative measurable function. However, to get this finite thing, you have to go all the way to the existence of the limit by simple functions, right? So Fm is the limit of simple function. That is what essentially you are using. Nothing more, nothing less. And that's the reason I said it's a big deal. Okay, so once you are here, then what you want to do, you want to take the limit inside. So if you take the limit inside, you are going to get the sum of Fn. You remember? Because limit of n goes to infinity Sn is your f, correct? So you want to do that, but when you do that, this limit inside, and you do not know how to take the limit outside, right? So if you take limit both sides, here the limit will give you the sum of the integration, right? And if you take the limit here outside, because you have taken outside here, then you need to get into inside. You need to take that limit inside. And how you do that? Again, MC, correct? And here is the argument. Since your Sn, as I said, I have this might be confusing, but this is your Sn, which I have said Fn again, no problem. Take it in that way. So this Fn is again going to be increasing, non-negative. So MCT would tell you the limit outside as n goes to infinity will get inside as n goes to infinity. And you know limit of Sn as n goes to infinity is nothing but sum of Fn. And that will resolve your problem. Therefore, taking limit n goes to infinity on the left and right, the left hand side along with this MCT argument would tell you this is going to be sum of Fn. And the outside limit is, of course, by definition, is sum of integration of Fn. And that proves the result. And so I tried to do this a little carefully so that you understand that nothing is free. You need to work a little more, even if it looks very easy, but you have to do some non-trivial work. So any question on this proof? And I show you the statement. And if you want me to scroll up and down, let me know. All right. Just to keep in mind that when you talk about MCT or when you talk about this chap, this result, you must assume your Fn are non-negative. Okay, and we use this on and off, so don't forget this part, because soon you are going to go to hit the general integration of general function. Need not be non-negative, it could be any value. Okay, so from at that point you have to be careful. You have to keep this in mind. What are the tools available and where you can apply. Okay. And here is a remark. So in the MCT, if you remember, we have assumed and also used extensively that Fn is increasing, sequence is increasing. And what I'm saying, that assumption is essential. You cannot get rid of that assumption. And here is a simple example. And I try to hide it so far, the Levegh measure of the real line, because I have not talked about it. We didn't have any room to talk about, but let me try to, so that's what I said. Suppose x equals to r. So x is the real line and mu is the Levegh measure. And the sigma algebra will be the Levegh measurable subsets of r. And I'm not going to define all of it, okay? But without that also, with some, as I said, with some, let's pretend that we know the Levegh measure on r, because I'm going to use this for a very special class, almost continuous case. Okay, so the Levegh measure on R, at least for the following simple and almost continuous function case. So it's almost continuous function. When the function is continuous, Lebesgue, Riemann, etc. all behaves well. All are fine. Okay. The point is to extend the class from continuous to, so continuous, you can say it's a Newton. Okay. It goes Newton's time. So it's all about pushing above, right? So you can pretend that you know a little bit of that, and continuous, etc. is going to be the same for the case of Lebesgue as well as Riemann. So here is the simple example. So define your Fn from R to R, not in infinity is not included. So you define Fnx for each n. Let's say that for each n. Define Fn by, so if your x ranges from, n is fixed, okay? So if your x ranges from 0 to 1 over n, you say n, and 0 otherwise. That means, so you look at 0 to 1 over n, you consider the value to be constant n. N is fixed in this case, constant n, and then it drops down to 0. That's the function. And since you know the characteristic function, Fn is nothing but n times the indicator of 0, 1 over n open. Okay, this is true for all n. That's how we define. Now you see, I mean, this tells you Fnx converges to 0 for all x. Well, so if you consider x from 0 to 1, you know, if f is outside 0, sorry, if x is outside 0 and 1, it is 0 anyway. So you have to worry about x in 0 and 1. So if x in 0 and 1, then if x is a fraction, and you know x will fall out of 0, 1 over n for some m in n, right? That means you are going to find a subinterval of from 0 to subinterval 0 to 1, m such that x will be larger than 1 over n, correct? And if x is larger than 1 over m, this definition will tell you if mx, and afterwards it's going to be 0, and hence that's what I said. If then by definition of we have, oh, I see, this is r minus 0, 1, so that's settled. So if this goes, if this falls outside of 0, 1 over m, then fn x will be 0 for all n larger than equals to m, and hence this will converge to 0. All in all, for all x in R, fn x converges to 0. That means fn converges to 0 pointwise, right? If this converges to 0 pointwise, then you know the limit of fn is 0 function. So we know that. So limit of fn is 0 function. Let's keep it over there. Now we look at fn. So one more time, the definition of fn tells you only there are only 2 points of discontinuity, right? At the point 0 and at the point 1 over it. So certainly it is Riemann integrable, almost continuous, and with some effort, which we have not talked about, but you can prove that this is also Lebesgue integrable. Okay, and the value of the integration is just like the Riemann integration. There is no ambiguity for this simple class of functions. So if you look at this guy, what is the integration of fn? The integration of fn will matter only from 0 to 1 over n, and you know it's just n times 1 over n. So the value of integration of fn is 1 for all n. If that's the case, then it's a constant sequence, so this will converge to 1, right? However, as we said, as we observed that the limit function is 0 function, so the integration of the limit of fn is the 0 function, which is 0, right? So this is 0, but that one converges to 1, and hence this MCT, the conclusion of MCT doesn't work, correct? So I have not written that. So, but that tells you that MCT fails for this. The conclusion of MCT fails. And then you argue, well, perhaps it's natural because the way we constructed our Fn is certainly not increasing. So since it is not increasing, we cannot expect the MCT conclusion. And that's where you want to keep this in mind, that Fn increasing is essential. I'll come to a similar kind of example at the end of the lecture. So any question? Okay. So this increasing part, the assumption that Fn is increasing seems to be important, essential. However, if you drop that, certainly the conclusion doesn't work. But even if you drop the monotonicity assumption, still you have something good. And that's what I want to talk about. However, we have the following without monotonicity, but we will not assume anything about monotone. Okay. However, we'll use MCT. And that's another big result, which is known as Fattos lemma. And you know what? Fattos lemma, if you think a little carefully, I think I pointed out as homework as well. Fattos lemma also gives you MCT. So MCT and Fattos lemma is accounted. Okay, so they are in quite equal status. There is not much of difference. So Fattos lemma tells you states the following, and again there is no increasingness assumption. So Fn is a sequence from L1. Then the integration of the lim inf of Fn is less than equals to lim inf of integration of Fn. Right? And as I said, if you assume Fattos lemma, a little work will tell you this inequality with another standard or trivial inequality would give you the MCT. And let's not get into that. Let's prove Fattos lemma. What it says, the lim inf preserves, integration and lim inf satisfy this inequality. That's all it says. And as I said, we are going to use the MCT. And here we go. Recall lim inf when you are talking about. What is lim inf of Fn? It is nothing but supremum of infimum of Fi, where I is larger than equals to k, and supremum is over k. So that's your sup of gk, correct? Where, for the sake of formality, gk is this part. So infimum, lim inf of Fn is sup of gk. What is gk? Gk is infimum of Fi, and Fi is I is larger than or equals to k for some fixed k. So the definition is clear and this is known to us. Now we observe, of course, since gk is increasing, so this is very typical of this lim inf and sup. So if since gk is increasing, we know that the lim inf of Fn, which is sup of gk. So sup of gk, where gk is increasing, is going to be nothing but the limit of k goes to infinity gk. Right? Since it is increasing, so sup of gk is going to be the limit. Right? Now, one more time, if you look at the definition, gk is the infimum of Fi for I larger than equals to k. So in particular, gk is smaller than equals to Fi for all I larger than equals to k. Why definition? And then we use this inequality. If this is less than this, then the integration is less than this. So integration gk is less than equals to integration Fi, right? And that tells you, if you, since this is true for all I larger than equals to k, then the infimum of the right hand side is also going to dominate your integration of gk. And let's keep it as star. Now one more time, since gk is increasing, limit of gk is lim inf of Fn. We know that, we observe that, and here I'm going to hit the MCT. Since this is true, then the limit of the integration of gk is going to be integration of the limit inside. So limit, when you take the limit inside, that means integration of limit of gk, then you get right hand side, and that's what you write. So limit of k goes to infinity gk is nothing but lim inf of Fn as n goes to infinity, that integration. And that's it. So what you have now, this fellow is equals to this integration of gk as k goes to infinity. But integration of gk as k goes to infinity can be, so integration of gk can be replaced by this. So you are going to get limit of k goes to infinity infimum of integration of fi, and again by the same reasoning that limit of k goes to infinity of this chap is nothing but lim inf of fn, because it's yeah, it's an increasing sequence. So this is an increasing sequence. So you can replace this by supremum, and that's the definition of lim inf, and that completes the proof. So any question? So if you think this carefully, the proof is very, very simple. It just introduce the MCT in right way. So if you start with all the assumption, you will see where you get stuck and where you really need something more. And that something more will be like MCT. And even in future, when you talk about measure theory, Lebesgue measure theory, in many places where you get stuck, there will be there will be three. The dominated convergence theorem is also there, but I'll not talk about it. Let's talk about these two. You are going to, well, that's also consequence in a sense of all this. So you are going to think about MCT or Fattos lemma. They are same. One of these three you are going to apply. Even I think if you do the Fubini's theorem, so if you do Fubini's theorem for the Riemann integrable integration, in the setting of Riemann integration, it's a bit of work, by the way. It's a bit of work because it has more jargon. But I think I'm saying right, although I have not taught this for long, but if you talk about Fubini's theorem, then I think you again appeal to MCT of one of these variant. Okay. And in MCT, you want to integrate double integration or triple integration and so on. You do not know how to do, but you go for iteration. Iteration is the way to perhaps compute, right? And so so Fubini theorem is very useful. And for Fubini theorem, when you talk about product measure, product domain, you want to, that Fubini theorem gives you the tool to compute. And I think the proof required one of these pillar results. All right.
Is there similar result for a sequence of non-negative functions for lim sup?
Sequence of
Non-negative measurable functions in case of lim sup? Like this Fattos lemma we discussed here, we got lim infimum of integration is dominant greater than by this like condition. So if we replace lim infimum by lim sup, so like similar.
So you are going to get something, because lim inf of fn is minus of lim sup of minus fn or something, right? So
okay, so
that way you can get something. Yeah. Okay. You understand my argument? I am not giving the answer perhaps, but what I'm saying, you can play that interchange, right? Lim inf has a formula in terms of lim sup, right? Using that with a minus sign plus outside, inside, etc., you can get something similar. But if you are asking other way around or not, that's not true. And in fact, there are examples where this inequality is strict inequality. So you in general, you are not going to get this as equality. Okay.
Okay.
And here is a theorem which you have seen in the simple case, where f is a simple function. We have seen this, and this is the general version. So what is the result? It says if your f is in R class, based on f, you define a function, set function mu f. So mu f is again a function from the sigma algebra to what? To 0 infinity. You see, when I talk about f is in R class, till this level, there is no need of any measure mu. But when I say, when this statement or any other statement picks up some measure mu, then you immediately must understand you are on a measure space. You understand? So I am right now on a measure space. to get f, you need only these two. But the second line tells you you need all of them, right? So we have to understand from the context. Fine. So like a simple function case, I'm defining this as integration of f d mu over E. I must assume, I have not said that, I must assume f is integral. And f is integral. You see, otherwise, merely a measurable function is not good enough, because measurable function, so what? Why it is integral? Okay, so it's a measurable function, and then you define for each e, you define the measure of so-called measure of f at e is the integration of f over e. Okay, this is the definition. Then, as I said, so-called, then you prove in reality that mu f is indeed a measure, and not only it's a measure, if you integrate a function with respect to the new measure mu f, you are going to get integration of gf d mu for each g in L plus. Okay, so this is let's see the. So we start with f and we have defined this, right? So let's do that. I have to check two things. One is empty set measure is 0 and it's countably added. So let's look at the empty set part first. So measure of empty set by definition is going to be the integration of df d mu over the empty set, correct? Now,
Okay.
yeah.
Sir, this theorem like means if f belongs to R plus and we are defining mu f of E equal to integrate over E f d mu. So just I want to ask you, so this definition we can interpret from distribution theory.
From which theory?
Distribution theory.
Distinguished theory?
Distribution.
Or distribution theory? Distribution in the sense of PDE?
Yes, sir. Yes, sir.
Yes, yes, these are related, but we'll not talk about this today. There is something called radon decoding theorem. I do not know. I mean, it's part of this series or not. This is the, so I'm just showing you a piece of result, which has lots of implication. Okay, and that's the reason I'm doing it, because this has lots of uses. But you are right. Okay.
Sir, can you tell me something about relate to from distribution theory and this definition?
Not today.
Something.
Not today.
Okay.
Not today. Because I want to finish this.
Okay. Okay.
All right. So the empty set part. So you integrate f over the empty set phi, and by definition, it is the soup of soup of integration of phi, simple function phi over empty set, and we know that any simple function over the empty set is the value is 0, and hence the supremum is 0, and hence this is equals to 0. Okay, fine. Now countable activity. So you want to start with a sequence of measurable function, and you take this intersection to be empty, disjoint. Okay, and you claim that the measure of phi. Sorry, what is this phi, by the way? It's f, right? Yeah. I considered the simple version. So measure of f on the union of En is equals to the sum of the measure on En. That's you want to prove. And remember, we have done this for simple function, where if is a simple function case, right? And proof goes very similar. Only thing you have to just bring that convergence thing, correct? So you set your E to be the union of En, disjoint union, and if that is the case, then the characteristic function on E over E is going to split, right? So the chi E is going to be sum of chi En, and hence chi EF is going to be sum of chi ENF, right? Since it is pointwise, etc., there is no problem. You can say that. Therefore, the measure, so mu f acting on E is by definition integration of f over E, fine. And then, like simple function, I'm writing instead of over E, I'm writing it over X, and then I'm writing chi EF. And here I'm asking why. Just this is a little homework. You use the definition of integration to prove that, like simple function, using the simple function property again, you can switch your E to chi E over here, and you can get this integration over X. So just this is a simple homework, please do it. So you do that, and then you are in chi EF. Now your chi EF is sum of chi ENF. All of them are in L plus, right? All of them are in L plus. So by the consequence of MCT, you remember that if you have integration of sum, then that is nothing but sum of integration. So this is sum of integration, and this, yeah, question. All right. So this is sum of the integration, and sum of the integration, and these terms, chi ENF d mu, is as per your definition. This is supposed to be mu f, right? This is supposed to be mu f. Let's see the definition one more time. Mu f is f d mu over E, right? So this is over. Oh, I'm sorry. This is correct. So this is chi ENF over X, and we know, as you observe, that this is nothing but you can pull down this En over here. So this is the integration of f over En, and that's the definition of mu f En. So this is correct. So up to this, it is fine. So what you have? You have mu f E, which is mu f of union, disjoint union of En, is equals to sum of mu f En. That's what you get. I have stressed this part only, which is mu f En. That's what you get. So this tells you that mu is countably additive, and hence mu f is a measurable. Mu f is a measure on X. Now, finally, you want to prove this equality. So you pick G from L plus, and I want to prove integration of G d mu f equals to integration of G f d mu. Okay. So finally, let G belongs to L plus. I want to prove what? I keep it over here. Integration G d mu f equals to G f d mu. Integration of G d mu f. Integration of G d mu f equals to integration G f d mu. This is what you want to prove for all G. So you pick a G, and that tells you there exists a subsequence. Again, you know that trick. So you pick up a sequence of simple function, increasing sequence, which converges to G. You do that, call it star, and then you just pause for a moment and observe something else. So you want to prove this, by the way. So what you do, instead of general G, first you consider G to be an integrated function, chi f, where f is a measurable set. Okay, so you consider G to be chi f, and if you take that G as chi f, then what will happen? Then actually we get the claim. Then we can see this equals to this. Why? Let's go from the right side. So let's consider G to be chi f, and let's compute the right hand side. So integration over x chi f d mu, the right hand side, right? So that's by definition, you know, since this is chi f, this is over x, that's going to be integration of f d mu. And by definition, this is nothing but the measure of f at the point, I'm sorry, mu f at the point f, on the subset f, right? And mu f at f is nothing but the integration of chi f d mu. Clear? So what you are saying, this equals to this if your g is integrated function, right? Now you observe, since a simple function is a finite linear combination of indicator functions, and you know at the level of simple function the integration is linear, right? So you can replace now the integrated function by any general simple function. Clear? The argument is clear. First you prove it easily for integrator, then you take the linear combination, and that's all simple function, right? So this equality holds for simple functions. So integration of phi over x equal d mu f equals to phi f d mu for all phi in L plus. Now we return to our business. So we do know for simple function this equality holds. Now I want to prove for the general f. For the general f, sorry, general g. For the general g, I consider this increasing sequence of simple function, right? And since phi n converges to g increasingly, and f is in L plus, you can easily show that phi n f also converges to gf. That means you can multiply both side by f, and you can also say phi n f converges to gf. And it's true because your f is positive. So you can say that phi n plus 1f minus phi n f is always positive because f is positive, and your phi n is positive, so it's going to work out, no problem. Okay, so this also converges to gf, and therefore integration of g d mu f, what you want to prove, integration of g d mu f is nothing but, since mu f is a measure, already you know that it is going to be equals to by mct. This is by mct. Remember, this is we can pass through the limit. So by mct we can take g is what, g is limit of phi n, so we can take the limit out. So this is going to be limit of n goes to infinity integration of phi n d mu f, right? And right now you are in the simple function situation, right? You are in the simple function situation. So simple function, we already proved integration of phi n d mu f is nothing but phi n f d mu. So do that. So you get that. Now you again apply MCT. So MCT second time, again apply MCT and take this inside, because this is going to be increasing sequence, blah, blah, blah. All is all right. And finally you say this is your GF, and that's what you want. That proves the result. So any question on this proof or the statement? No? Okay. So in this case, you have used MCT 2 times, I hope. Only 2 times. Finally, a remark. The remark is very simple, and it should draw your attention. It says this MCT does not hold for Riemann integration. You see, if you look at the MCT, let's go to set 5. If you look at the statement of MCT, it says that if you have an increasing sequence of measurable functions, non-negative measurable functions, okay, then it is the limit, the integration of the limit is limit of the integration. This is what MCT says. And what I'm saying now? I'm saying, oops, why this is set 6. Okay, what I'm saying that doesn't work. I mean, that result doesn't work in the setting of Riemann integration, and here is the result. So what you do, you look at 0, 1 closed interval, and you take all the rational number in 0, 1, and you know it's a countable set. So you enumerate them and call them Rn. If I think it's you take it increasing fashion. Okay, so let's do that. Rn is increasing. And then you do the following. For each n, you define Fn from 0, 1 to 0 infinity. Actually, it's never going to take infinity. So you can take in open. And by the way, for Riemann integrability, you cannot talk about infinity. Clear? So we are not allowed to talk about it. You are not allowed to include infinity. Fantastic. Otherwise, it's not a fair game, right? I mean, Riemann already say you have to assume bounded, and if you say no, I will only work on unbounded, that doesn't work, right? It's not fair game. So you take bounded function, but here you define tactically. So fnx for each n, you define fnx as 1 if your x is one of those R1 up to Rn. Okay? And 0 otherwise. Okay. So one more time, your fnx is 1 if x is one of these finitely many R1 up to Rn, or 0 otherwise. So how many places fn hits non-zero term? Only up to n, right? And beyond it's 0, or everywhere it is 0. By construction, if your n is less than, if you consider n less than equals to m, then fn will be less than equals to fm. That means fn is a monotonically increasing function by construction. Clearly fn is bounded. Clearly the point of discontinuity of fn is finitely many, n, correct? So it is Riemann integrable, non-negative by construction. And clearly, you know that if it is 0 everywhere except finitely many endpoints, then the Riemann integration, upper sum, lower sum straight away tells you it's the value of the integration is going to be 0 for all n, right? So the Riemann integration is 0. Now you ask, where does Fn converge? Well, Fn converge to precisely chi of the Rn, right? So chi on the integrator function on the rational inside the 0, 1 closed interval, you know that's not Riemann integrable. So the limit function is not Riemann integrable, and hence this equality doesn't make sense at all. Why? Because this doesn't make sense. The left hand side doesn't make sense. Oh, I said right hand side. It should be the left hand side. Left hand side, right? The limit fn doesn't make sense. So the left hand side is occupied. And that's all about it. So this is where I like to stop. However, here is some exercises, and some of them will be done in your tutorial. Not all. Some of them you take. And I have 3-4 minutes, and I give you a quick outline what we did in this past 6 lectures. And I think that place I would stop, because to warm up, to remind you what you have done, so that you can start, you can have a fresh start with Shachi Srivastava's lectures, series of lectures. Okay. All right, so we started with power series. It's a very important component in analysis, real, complex, harmonic, anything you wish to talk about. And we pointed out Hadamard theorem that tells you straight away a region of convergency. And then we went on talking about exponential functions, sine of z, cosine of z, and many interesting properties of exponential function. And we celebrated this statement of Rudin that exponential is the most important function. Some people say one of the most important functions. That's not what he said. He said the most important function. So we gave some time to honor his comment, and which is very, very correct. It is correct because Rudin said. When Rudin says something, you have to be really careful. But also my experience tells, and perhaps yours, and when you do the research world, you will see it is indeed true. The exponential is the most important function. Okay. Not polynomial. Polynomial is a good guy, but after that level, is exponential is the one. Then we introduced sigma algebras, and then we introduced Borel sigma algebra, just bringing topology on the measure on the set where you are talking about algebras, right? And then we talked about the sigma algebras generated by subsets. For instance, if you have a subset of power set P, power set of X, then sigma of F is the smallest sigma algebra containing the smallest sigma algebra containing F, and we know, if you remember, it is the intersection of all those sigma algebra which contains F. Simple. Okay. Then we talked about Borel sigma algebras, which contains G delta F sigma. The real reason is that to enlarge the sigma algebra, I mean, to realize that the sigma algebra is much larger than your standard topological space or topology, an open space, right? Then we pointed out that even your sigma algebra might look massive and it's enormous, but still you can talk about generators. So this idea is very important. Then you went on and say that your sigma algebra could be generated by open intervals, like these and so on. Or even you go to minus infinity to plus infinity, you have similar type of so-called smaller set, which generates your massive sigma algebra. So don't forget, sigma algebra is a massive set, right? But you have control over the generator. And that's the key idea of defining measurable functions, which we did, as I pointed out, measurable space and measurable functions using this generating properties. We had a lot of control over that. And while doing all these, we realized that the inverse function, if you have a function f from x to y, the inverse function has a very powerful, it has lots of powerful properties, but mostly it is this. And that's where I think the measure theory is standing on. F inverse is this map from power set of y to power set of x, and it behaves well in the sense it goes well with intersection, union, and difference, right? And we pointed that out. Then we talked about C-valued measurable functions, and we said that this forms an algebra. And today itself, I warned you that if you want to do that from on 0 infinity value closed, it's okay. But minus infinity to plus infinity, it's not going to work out in that extent, right? Because plus infinity minus infinity doesn't make sense. Then we talked about sup, inf, lim, sup, lim, inf, etc. And we said the measurable, if you take a sequence of measurable function, then sup, inf, all this thing works fine. And then we pointed out that simple functions actually converges to measurable function. Well, non-negative, by the way. So it's at the level of, is it right? Actually, it doesn't require non-negative. I think in some of the lecture you will realize I did it for non-negative because I was in the Rudin setting, right? It doesn't have to be non-negative. You can go beyond for general function. Then you talked about measure space. So this triple, what we called as measure space, it's measure here, defined on the sigma algebra S. Then we defined the integration of simple function, and from there we considered the supremum of this guy to define integration of non-negative measurable functions, right? Then we talked about two giants like MCT and Fattos lemma, and finally we proved very interesting result, which says that if you have a measure and if you have a measurable function, you can always come up with a new measure. So this is what I said as new from old. And that's where we stopped for these six lectures. And by the way, here are some homework. I think one of them I wanted to tell you. Perhaps, okay, it may not be here. It may be in the. Yeah, this is something very interesting. You must work out. You must work out the level measure theory in the sense of counting measure, which is very important. Very useful. No, I think it is in the other set. Fine. So anyway, so this is where I want to stop. thank you very much. Thanks for your patience. Yeah, I'm done.
Hi, Jaydeb. So, all right, so let me just say a little bit here. I just wanted to thank Jaydeb for this set of lectures, really wonderful lectures. And I personally enjoyed very much that, the way it started by asking questions and looking at what is missing when you try to do Riemann integration. And then gradually, you have something which are missing, things which you want to improve. And out of that confusion, gradually some order emerges. And that's very nice. And at the end, we have this very nice, neat summary where we began with so much of bit of chaos and wondering, how things can possibly be okay. So thanks, Jaydeb, for this really nice set of lectures. Thanks also for agreeing to give these lectures at such short notice. And I had made a special request to Jaydeb that if he could give the first set of lectures and get us off to a good start, that would be really nice. And he agreed to that as well. So yeah, it's really been wonderful. Thanks so much. And
Thanks so much.
Yeah.
Thanks. Also, I want to thank the audience on board, because I think they made this lecture more useful to me. I admit I'm not happy. I'm not satisfied. I'm never satisfied. Okay, I'm never satisfied with my lecture wherever I go. But I give a lot of time for my lecture, no matter if it is school lecture, college lecture, or research lecture. But this online is very, very uncomfortable. How? And I was not very positive about it. But I can guarantee that the audience is very, very nice. They have really participated, and that's how I teach. On board, I think you also agree. That's how we teach, right? We want the student to come. Instead of reading or writing, we expect you guys to come out, and you have done that, and that makes this thing more interesting. And I can tell you, I have also learned from you, even out of these 6 online lectures. So thank you very much. And I'm going to again certify that you're going to have more interesting speakers, better than me, I am pretty sure. And they're going to enjoy the time with you. Please hang around, and your effort is more important than me, I can tell you, because you're sitting, and not only that, you are catching my mistakes. It's not easy, because I'm scrolling this file up and down, and many of you actually pointed out that I have done mistake, these, that, whatnot, and I appreciate, really appreciate. Thanks a lot. And if you have any mathematical questions. And I'm going to